In this video, we will learn about acid-base chemistry, specifically about pKas, and this is going to set the groundwork for looking at organic reactions. So, acid-base reactions are really important in organic chemistry because it turns out that acid-base reactions make up a good portion of the types of transformations we're going to see in organic reactions. So, if we're turning reactant A plus B into product C, along the way, we're going to often do an acid-base reaction. A second reason that acid-base chemistry is important is that there are many features in organic reactions that are analogous to those in acid-base reactions. So understanding acid-base reactions first can go a long ways toward helping understand organic reactions. So a generic acid-base reaction looks like this. We have molecule HA plus molecule B with a lone pair here. This hydrogen, or this proton, is transferred during the acid-base reaction. The identity of these species are, so the HA is the acid, which turns into, in the product side, the conjugate base, and the B species is the base, that turns into the conjugate acid. One important thing to note here is that I'm color coding by the fact that this is an acid, right? So HA is an acid, HB is the conjugate acid. I'm not trying to make you think that somehow A transformed into B here. So an acid-base reaction is one of the simplest chemical reactions that you'll see. What's happening here is that the pair of electrons that is shared between the hydrogen and the A part of the acid is going from being shared to being unshared in the conjugate base. The pair of electrons in the base is going from being unshared to now being shared in the conjugate acid. And of course, finally, the proton is initially bonded to the A, now it's bonded to the B in the products. So when we're thinking about acid-base chemistry, there are a few important questions we want to be able to answer. So the first one is, given an acid-base equilibrium like this, we want to be able to judge relatively quickly which side is going to be favored in the reaction, and also by how much that side is going to be favored. A second type of question is, given two species, which one of these two species is the more basic one? Because that's important, because the more basic one is the one that's going to be more reactive. And then similarly, given two species or two protons, which of those two is more acidic? Again, that's important because the more acidic one is going to be the more reactive one. Before we look at how to answer those questions, it's necessary for us to define the term pKa. So pKa comes from just normal equilibrium math, where we're treating the reaction where an acid dissociating into a proton plus a conjugate base right here has an equilibrium constant that instead of KEQ, we call it specifically the Ka, or K sub A, K acid. If you're looking at the math, that should look like the concentration of proton times concentration of anion divided by HA here. Because of the way that these equilibrium constants have been found to vary over large orders of magnitude, so over 60 orders of magnitude, it just is much more convenient for us to turn this into kind of the log form and use a pKa instead. So that's the negative log of the Ka. What that essentially does is it takes the exponent on the Ka here. So if this is 10 to the 20, then we'll say pKa equals 20. Give you an example of this range. So here I have three types of protons in three different molecules, and just giving you the pKa ranges here. You can see that this one has a pKa equals 5, this one is 50, so extremely high. This one's negative 7.2, so extremely low. And so when we use our pKas, there are two things we want to keep in mind. So one is that if we're comparing two protons, the one with the lower pKa is going to be more acidic. So if we're looking up here at these three molecules, the species right here is going to be the most acidic, or this proton specifically is going to be the most acidic out of everything that's shown here. The opposite way of thinking is to think about the strength of base. And so what we want to know is that a more basic species has a conjugate acid with a higher pKa. And so this can be very confusing because we're always trying to reference two acids. The reason is that this is much easier because we only have to deal with pKas. If we had to also deal with pKbs, or kind of the basic version, then you have two sets of numbers and that gets very confusing. So again, For bases, we reference to the conjugate acid and look at those pKas. So as an example, let's look at these two bases right here. Both of these will react with a proton to become protonated. And when that happens, you get to these two conjugate acids. So here, if we look at the pKas, we want to pick the higher pKa conjugate acid as coming from the stronger base, which is this species right here, or the molecule pyridine. We just looked at the reaction where a molecule HA dissociates into H and A minus and use that to make some judgments. Now let's look at when we're actually doing an acid-base reaction between something that's acidic and something that's basic. The base that I'm showing you here is called an organolithium because there's a lithium and it's drawn as covalently bonded to the carbon. Turns out that's a more accurate way to draw it, but it's okay in your mind to think of that bond being a little more ionic. So looking like this, and the same thing for the right side in the products here. People will often write it out as if it's covalent, but it does have a lot of ionic nature to it. So when we're evaluating this acid-base reaction, what we can see is that the proton goes from being attached in the methanol to now being in the butane. Those are the acid and conjugate acid, respectively. So then what we do is we compare the pKas. The pKas tell us that the butane has a much higher pKa, so we pick the right side of this reaction as being favored. Once we pick which side of a reaction is favored, the next question will be how much that side of the reaction is favored. And there's a lot of gray area here, but we can have some very general guidelines. So what we'll do is to take the difference in pKa of the conjugate acid and the acid in our acid-base reaction. Naturally, if those are equal to each other, or delta pKa equals 0, then this equilibrium is going to be equal to both sides. We should expect equal amounts of HA and HB plus in our reaction mixture. A rule of thumb is if the pKa difference is greater than 10, so the product has a pKa at least 10 or more larger than the reactant acid, then we consider this reaction as essentially being a single direction and going all two products, and that in our reaction mixture we'll have only products. So this should make sense because if delta pKa is equal to 10, that means the right side of the reaction will be favored by 10 to the 10 to 1, and so that means that 10 billion of your molecules will be on this side, and only 1 out of 10 billion times will you be able to even find one of these HAs. The protons will essentially always be on HB. Of course, the same is true if delta pKa were to be less than negative 10, so that's just going the other direction now. And this acid-base reaction should favor essentially exclusively the reactant side. What's tricky is in between. So what we'll say is that there's these gray areas. So between 0 and 6 delta pKa, that's going to be mostly products. And if it's between 0 and negative 6, that's going to be mostly reactants favored for this delta pKa. But this range right here, I kind of give you two numbers here because different resources will give different expectations for this number. And also the specific reaction temperature and conditions can kind of affect which of these numbers is a little bit more accurate. So this chart's a little bit much to look at, so it's helpful to have a simplified view. And so that's here. Essentially, if our absolute value of the delta pKa is greater than 10, then only one side of our acid-base reaction can be thought of as being present. The other side is essentially negligible. If that difference in pKa is between 0 and 10, then it's safe to think that we have a bit of both sides and that the side with the higher pKa is favored. Now let's look at the factors that influence the pKa of a given proton. The general rule of thumb is that a stronger acid will have a more stable conjugate base. So let me pull up an acid-base reaction here. And what I'm saying essentially is that if we're thinking about the acid on the left here, in order for it to be willing to dissociate and give up this hydrogen, that is only going to happen if the lone pair that was initially shared here and becomes unshared in the conjugate base here, this lone pair needs to be stabilized, right? That's the sacrifice that we're making in order to transfer this proton somewhere else. So another way to view this is that our strong acids are going to be relatively unstable, and our stable conjugate bases will have a lot of factors that stabilize this lone pair that is now formed instead of having it bonded right here. So let's go through some of these factors. I've tried to list these in a very rough order from most to least important. This is not a hard ranking whatsoever. There's plenty of examples that can go across these rankings. All right, so the first thing is that when the proton we're thinking about is attached to an atom with a positive charge or a partial positive charge, then that proton will be relatively more acidic. So here's an example looking at just water, having pKa about 15.7, versus protonated water, or H3O+, that pKa is negative 1.7, because this oxygen is positively charged. Next, protons that are attached to more electronegative atoms will generally be more acidic, and so here's a trend kind of going across a periodic table, and this should make sense because if we're thinking about the lone pair that's being formed from the shared pair of electrons between the proton and the electronegative atom, then the more electronegative atom will better stabilize the lone pair right here. So going down the periodic table, the trend follows polarizability. Protons attached to more polarizable atoms will be more acidic. This is because if we look at the conjugate base, so the anion, so let's say the fluoride, chloride, bromide, or iodide, the iodide has a much larger atomic radius and a larger ionic radius in which it can delocalize the lone pair of electrons that is left behind after the acid is dissociated. Another factor is that the hybridization of the atom that the proton is attached to can matter. So if we're comparing the same element but in different hybridization states, then what we find is that the more S character there is, the more acidic the proton we're thinking about is. This is because we think of the S orbital as being a little bit more electronegative than p orbitals for a given element. And so the trend is pretty clear. And it's a very drastic jump from sp2 to sp, less of a jump from sp3 to sp2. Other factors include resonance stabilization of the lone pair in the conjugate base. So here I'm showing you an example where this pair of electrons would not have any resonance stabilization if this acid was dissociated. This pair of electrons right here would have some resonance stabilization because it's benzyl to this benzene ring here. And finally, this pair of electrons has a lot of stabilization because it actually makes this ring here more aromatic. And so that's reflected in the high, less high, and much lower pKa values. Just in case that's not totally clear here, I have the conjugate bases for the right two molecules just to let you see that we have resonance stabilization of this lone pair. We have aromatic stabilization here. The electronegativity of elements can be felt further than one bond away, and the inductive effect. And so the inductive effect can be significantly stabilizing as well. If we compare acetic acid to trifluoroacetic acid, we see a 5 pKa unit change, so a 10 to the 5th difference in acidity. This is because the conjugate base of trifluoroacetic acid, it has a negative charge in a lone pair on the oxygen, but that's stabilized by the electron withdrawing nature of these fluorines here that is missing in acetic acid. So we have a much stronger acid because the conjugate base is more stable in trifluoroacetic acid. The last factor, which is maybe a little bit more subtle, is that solvation of ions is extremely important for stabilizing ions. So if you're starting with a neutral organic molecule, in general, it is not going to be stabilizing to separate the charges and create formal negative and formal positive charges. So in order to achieve that, we need to have some factors that stabilize those ions as they are kind of sitting in the solution. The way that happens is that solvent molecules will arrange themselves around ions in order to have dipole-dipole interactions or formal charge interactions or hydrogen bonding interactions as a form of stabilization. But the ability to do that depends on how easy it is to surround the atom that has that formal charge on it. So for example, I have an alcohol here, so this is just methanol, that has a pKa of 15.5. Now if I go to terbutanol, so this is also an alcohol, so still a proton attached to an electronegative oxygen, that's all attached to carbon, that's all kind of the same. The only difference now is that these extra methyl groups out here are sterically very big. That makes it much harder for a solvent molecule to sit, let's say, over here to stabilize the conjugate base. And because of that, this conjugate base is less stable. That raises the pKa of the acid because the acid would rather not react and become so unstable relative to the methanol molecule. On this note of solvation, I want to make one final point, which is that pKa values that are reported in these large data tables accessible online, these pKa values are solvent dependent. And why that matters is that organic chemistry happens in many different types of solvents. but pKa values are usually reported in either water or DMSO, which is this organic molecule, as the solvent. So the problem there is that if you're thinking about numbers that come from these solvents, they may not extrapolate exactly into whatever solvent that you're actually dealing with. As an example of that, methanol in water has a pKa of 15.5, so that's referring to the dissociation of methanol into the proton and the MEO with a negative charge, which is called methoxide. In DMSO, that equilibrium constant is much higher. It's much more in favor of the reactants. So methanol is going to be much less likely to dissociate in DMSO than it is in water. And so that's a huge factor when it comes to thinking about reactions. The reason for this is that we have to think about how these solvents stabilize ions. The water and DMSO are both polar molecules, and so they are able to then stabilize this ion through dipole-dipole interactions. However, only water has the ability to hydrogen bond with the methoxide, which is this species up here, that is formed in the conjugate base. DMSO doesn't have any hydrogens that are capable of doing hydrogen bonding, so it can't contribute hydrogen bonding. That is the reason why it's easier to form methoxide in water than in DMSO. So a term that will come up in the future when talking about organic reactions is that water is a polar protic solvent, where protic refers to the fact that it has a proton it can hydrogen bond, while DMSO is a polar but aprotic solvent, meaning it doesn't have a hydrogen that can hydrogen bond. For now, the key things you want to take away from this video are that solvent does matter, and that there are a lot of different factors that can go into helping predict whether a given proton is more or less acidic than another, and analogously, whether a given lone pair is more or less basic than another.